Hey everyone, in today's video we're going to be talking about bounded area. Specifically, that's the area between two or more functions or relations. So far when we've integrated, that's been giving us the area underneath one function and the x-axis. Or, as we've discussed a little bit, it doesn't have to be the x-axis. It could, of course, be a different one as well. Today, again, we're going to look at finding the area between two or more functions or relations. So our first one here is a no calculator problem, although often this is a calculator task. So let's see. Without using a calculator, find the area of the region bounded above by, here's a linear function, and bounded below by a quadratic. So first off, let's just kind of sketch what that would look like here. Okay, so the linear function has a y-intercept of 5 and a slope of 1. So it is probably doing something like this. Let's move that little point down. Ah, dang it. There we go. So let's call that one 0, 5. And then the quadratic, well, I do see it's x squared plus 5, so I know its vertex is going to be up here at 5, and I know it's going to be doing something kind of like this, right? Quadratics curve a little bit slower than linear functions, at least for the first unit that they pick up. And there's going to have to be some intersection point over here. If you have great knowledge of the basic functions, you might already know where this intersection point is. But as a strategy to find it, here's what I would do. Since both of these equations are y equals, or whatever, we want to know where they have the same y value, right? So let's set them equal to each other. Let's say, where is the linear function equal to the quadratic? Now this will give us an x value, but then we can turn it around and solve for y if we need. Actually, we won't need that y value. We're going to need the x value here on this problem, but in a future problem, you could need the y. Let's see. Okay, so let's just do some subtraction here. I'm going to move over the x. I'm going to move over this 5. So we have x squared minus x, and then 5 minus 5 is 0. Going back to my algebra days, I think we'd have to factor out an x. And then we would solve for each piece, set them both equal to 0, since it's a product. Okay, there's our intersection points, 0, which we already knew, and 1. So specifically this point is 1, 6. So what are we going to do to find this area in red? That's what we want. You don't have a good way to answer that question. Here's what I want you to think about. You don't have a good way to tell me or answer that question. That's what I should say. So here's just y equals x plus 5. And if we were to integrate x plus 5 from 0 to 1, we would get all of this area. And then, if we were to separately integrate, actually, I want a little more room here in the future. I'm going to move this over here. If we were to separately integrate x squared, whoop, that's not a good sketch. Let's try again. If we were to separately integrate this one, the quadratic from 0 to 1, x squared plus 5, we would get this area. Well, since we really want this stuff that's in between the two, good news, we're just going to subtract these. There's two different ways you can actually do this. You can do two integrals, or you can do one. So you could just do integral 0 to 1, x plus 5 dx, minus integral 0 to 1, x squared plus 5 dx, because this would get you the blue area. This would get you the green. And then the difference of the two would get you the red over here in my left diagram. But we have to come up with two antiderivatives if we do this, right? Because the limits of integration are the same, we're going from 0 to 1, 0 to 1 both times. Our variables match, dx, dx. You can condense this integral because it's just one minus the other. So you can simplify this into one single integral from 0 to 1 of x plus 5 minus, and you just have to make sure you subtract both things here, the x squared plus 5. which, again, you can clean that up a little bit. So it'd be like, and I'll write it in standard form too. Well, no. Let's just say, okay, so we have our x here. Yeah, you have a plus 5, then you have minus 5 later, so that's gone. So minus x squared. And that would be it. A little bit less work, right? Because now antiderivative power rule, minus x. Evaluate from 0 to 1. Hey, plugging in 0 in both those places does nothing. So you plug in 1 in both, you end up with a half minus a third, which, well, I think we're going to have to reach for sixths to work that one. I think we'd be left over with 1/6. So hopefully that's believable to you. Again, what are the key things we had to do here? We had to identify the points of intersection, the points where the function itself, or where the bounded area starts and stops. We also had to identify which function was the top one, which one bounds above, and which one bounds below. Now, we were kind of told that in the problem, but it's important because when you integrate, we need to make sure we are doing the bigger area, the top area, minus the one that bounds the bottom. Because basically what we're doing here is you need to make sure you're subtracting out all the excess stuff, all the stuff we don't care about. That green area over there would be all this green area right here underneath the red. Okay, hopefully that's believable to you. Let's do another. So this time around, we'll use a calculator to help us out. The region is enclosed by the graphs of y equals cosine 2x and y equals, oops, hey, this fell off the line. It's x squared minus 2. So again, you could visualize this just based on your knowledge of the 12 basic functions in theory, because you took my pre-calculus class. You should know that the cosine function, is going to do something like this, right? Whoops, I didn't really get that y-intercept in a good spot. Well, it's got a y-intercept, at 1-ish. This 2 is just going to affect the period, how often it repeats itself. And what? It's going to do something like this, and it's going to come back up. Something like this, and it's going to come back up. At some point, this is just a sketch. And then x squared minus 2. Well, it's going to be a parabola somewhere. I don't know where exactly the intersection point is going to happen. Maybe the intersections are down here. Maybe it's a little higher up. So, okay, I think we're going to need to reach for graphing calculator on this one. Let's see. So, first off, let's graph it. And, all right, what do we got? We got trig cosine, nope, don't care, of 2x. And then I'm going to hit the tab button to get a second graph on the same page. I'm going to press x squared. Okay, so the intersection point happens kind of in the positive area. Good thing we didn't, jump to conclusions there. So kind of let's write out some of our steps here, actually. I wish I hadn't used all that space on my sketch. Oh well. We know it's going to do something like this. Okay? So we're going to have intersection points up here in the positive region. What do we need to do? For any bounded area problem, like we did up here, we needed to figure out which function was on top, which one's on bottom, because I need to know which area I'm going to subtract. So determine the top and the bottom functions. So in this case, I know the top function has to be the cosine 2x. The bottom function has to be the x squared minus 2. I'm now suddenly realizing I did not do the minus 2. Okay. Good news. We'll just hit the tab button. I'll go up, minus 2. Heck. Okay. Easy fix. Easy fix. Oh, not easy fix for you. Easy fix for me. Zoop, it's gone. I'm sorry. There I was thinking, oh, it's my notebook that's wrong. I made a mistake when I sketched it earlier. Nope. Okay, there's our intersections. Okay, regardless, here we are. We've identified the top and the bottom function. At some point, we need to figure out exactly where the boundaries are, because that's going to be our limits of integration. See how here we went from intersection point to intersection point? Barring anything super weird happening in the problem, like which functions on top and bottom changing, yes, that can happen. We just typically integrate from the left to the right. So we need to determine limits of integration. Which we'll say is usually intersection points. Again, the only time it's not the intersection points is if which function is the top and the bottom switches. Which actually, well, even there, it'd actually be an intersection point, right? It's just mentally in your head. Yeah, nailed it. Okay, so handy dandy calculator time. Intersection points. Why I didn't do that? I mean, I did that, but I didn't want to do that. Okay, I just wanted to get you out the way. Get out the way. Yes. I want you to get out the way. Yes. Okay. So intersection points, hit that menu key, analyze graph intersection. I know it's been a while, but there it is. When it says lower bound, I need you to click somewhere to the left of the intersection point you're looking for. Where it says upper bound, click somewhere to the right of the intersection you're looking for, but not so far away that it snaps over to the other one. So first I want this one on the left. And this is not many digits, right? We said in calculus, your final answer needs to be accurate to at least 3 decimal places. If this is something I'm using to generate another number, I better go float some more digits. So let's see, display, let's go 6 or something. I don't know. 6 sounds good. Hey, there we go. Look at all that. Okay. Now, let's write that down on the page real quick. So our intersection point would be x equals negative 1.15296111. And using your knowledge of the basic functions, you could say, aha, Mr. Doolin, these are both even functions. Therefore, it needs to be symmetrical. The other intersection point would be positive 1.15296111. You don't believe me? Check it. Menu, analyze, intersect, lower, upper. There it is. Same thing. Hey, but get this, though. We're like going to use that number in our calculator. And why write it down and have to key it out again? If you tap on it, now you'll have to use your touchpad and then tap on it. If you hit the variable key, but not the variable, we're going to store this number. If you, at the end, whoop, don't highlight it, just have your cursor in there. If you hit Control Variable, it'll use the blue ink, which uses the store function. Pick your favorite letter that's not X, Y, or Z. So let's just say store as A. Press, excuse me, that's supposed to work. I do this all the time. Are you serious? This doesn't work? Nope, we're troubleshooting that. This is the time saver. We got to save our time here. Okay. So I have done nothing different other than I opened up a new graph window and regraphed our functions. And you notice if I just put my mouse over, so you'll have to use that touchpad, put your mouse over the X value you want, just click once. Do you only not work when I'm recording the screen? Because I'm going to be so mad. Oh my, it's not supposed to highlight. I did this before I fired up the recording. I did it on my Mac. I did it on my Nspire. Why do you only not work when I'm recording? God bless. We're going to come back. Okay, well, this is ridiculous. Basically, you should be able to put your mouse over the number you want. If you click once, it should put the entire number in just like a blue box. It shouldn't put the cursor in there. It'd just be a blue box. And if you hit Control Variable, so that activates the store function, it'll ask you, hey, what letter do you want to store this in? Pick any letter you want, you press enter. That is not working for me. If it doesn't work for you, here's a workaround. Just like on your computer, if you hit Control and C, it will copy the number. So if it highlights the whole number in blue and it gives you that cursor, if you do Control C, it'll give you that number copied in your clipboard. And then if you open up a calculator page, hit your integral, numerical integral, then if you do Control V, again, just like your computer, it'll paste. So that's what I'm going to have to do for this video. I'm going to go back to my graph. I'm going to, oh, I didn't get the other intersection point because I redid this. click it once. It worked, it worked. Okay, see how it's just highlighted in blue? The cursor isn't there. I'm going to go Control, Variable. It's asking what I want to store it as. I'm going to store it as B because I would have done the other one with A. Make sure you don't store them as the same number. I'm going to go back to my calculator window. And again, if I'd copied it, I could paste it here. Since I stored it as a letter, I'm just going to put in B. That's fine. Then, when we actually integrate, we're going to do the functions. So I'm going to come back to that in a second. We have just a little more to do over here. Go back to touchscreen mode real quick. Okay. So, okay, gosh, I thought I stopped recording there for a second. Last thing is, sometimes people get bugged by the idea of, well, up above I just said it was top minus bottom, but now one of my functions is underneath the axis. So what are we to do here? Here's just what I want you to think about. You know how integrating is really, you're just making a whole bunch of rectangles somewhere? What I want you to do is to make a rectangular slice of the whole area somewhere, something like this. And if we're planning on integrating with respect to x, I want you to make it an infinitely thin amount of x. So our width there is dx. But the other thing that's interesting is what's the length of that going to be? Because again, up above, both of these were above the x-axis, so it was no problem. Here it's kind of weird to think about, oh, well, I got some positive area, I got some positive area, got some negative area. What am I going to do here? Let's think about the length of that slice. So from top to bottom, what would my length be? Well, it would be the height of the top function, cosine of 2x, because that would get me this part. And then, well, if I was looking at just the bottom here, if I just did the y value of that one, x squared minus 2, that's going to give me a negative number. But I need a positive for length. So I'm going to subtract it. That way I'm doing minus a negative to get out a positive value. That should give me a positive number for length. Well, as it turns out then, we're still doing top minus bottom, which is exactly what we did up here, top minus bottom. So even though it's on the wrong side of the axis, whatever, it's okay. Doing integral of top minus bottom functions will get you a positive area. Random fact, I'll get this down at the bottom of the page once we're all done. Bounded area should always come out positive because it's an amount of area between two places or more. So, 3, integrate. So in our calculator, again, make sure you're getting those however you want to get these numbers into your limits. Either store them as variables or copy paste 9611 or type them out the long way. You know what? That works too. Top function cosine 2x minus x squared minus 2. Top minus bottom. dx. We'll hit the integral. We'll get us a number. Showing you over here. Now these functions are pretty trivial, right? There's only like 2 things in them. It's cosine of x or cosine 2x minus a quadratic. If they're anything more abstract, again, to save yourself some time, look at that variable key. Remember, so in my first failed graph, the cosine was f1 and the quadratic was f2. So what I can do here is I need to do the cosine function. So I'll just call function 1, it was a function of x, minus variable function 2, which was also a function of x. And then I will close my integral. There's a value. This is the exact same thing as doing it out the long way. So if I did, I'd have to do cosine of 2x minus x squared minus 2. Exact same thing. So hopefully that convinces you. So the function keys again can be a shortcut if you've already graphed the functions. 4.332. And again, I promised you this at the bottom of the page somewhere. Bounded area should always be positive. Because it's just the amount of area between 2 places. So we're not worrying about above or below or anything. One more trick on your calculator. Now, this does require you to have received a software update at some point in the past, like 2 or 3 years. So if you have a hand-me-down calculator, you may not have received this software update. If not, well, I can give it to you if I ever see you in person, or you can download it from the internet. You just got to plug your NSpire into your computer. If you hit that menu button one more time, Analyze Graph, look at the second to bottom option here, bounded area. Pretty nice. Lower bound, I think it's smart enough to snap to, hey, what are you doing, Mouse? Come on. There we go. So it's smart enough to snap to the point of intersection there. So go ahead and click there. Upper bound, again, it should be smart enough to snap to the point of intersection. And I don't know where it put it. Where's my answer? Here it is. There's my answer. 4.33128. So again, if calculator's loud, you can check your answer right like that. Okay. That was a lot of time for one page, but that's no big. We only have 2 problems left, and it's not a whole lot new. For the second one, I'm just going to show you why sometimes we might integrate with respect to a different variable. So first off, the giveaway on this problem is I have x equals. But even if it was not that, if we were just thinking about our normal top minus bottom logic, so here we go. I'm going to just bold this in a little bit so it's easier to see. There's my blue. There's my purple, and then there's my green. If this was not x equals, or you went through the legwork to solve and get y equals. With this one, you'd have a plus or minus square root of stuff, right? Because it's y squared, so you'd have a plus or minus squared in the end. That's why I have the blue going up, the purple going down. You could find this using dx slices. And what I mean by that is, remember how over here I said I want you to make a little infinitely thin slice? I always said if it's vertical, it'd be dx. So the tough part here would be which one is your top and bottom function changes once you get to this intersection point. So from -1 to 0, you have the blue function minus the purple function. Then once you get to 0, you have the blue function minus the green function. Kind of difficult, but can be done. The other way to solve this problem is, I just needed, give me one more color in here. And something that'll pop. How about like will this yellow work? Oh, that's thick, but it'll work. What if we sliced it the other way? There we go. This will be better. So instead of doing dx, what if I said my infinitely thin little slice there is some amount of dy, some differential height instead of width? Then I would still need to know the length of my rectangle, but we could integrate with respect to y instead of x. That's going to simplify something because, so like we said with dx's, it was always top minus bottom, right? It was always top minus bottom. With dy's, it would always be right minus left. So we'd be looking for width instead of length here. So let's think. My right function is going to be this linear one. That's kind of giveaway on the picture, right? The one that's not curving. So my right would be the y minus 1. Okay, I got to get out of this yellow color. I don't know how well you'll like that. So there's my right function. There's my left function. And we'll just, you can label this with W. You don't have to. My left is the y minus 2 squared minus 1. So my width, the width of this rectangle with height dy is going to be 1 minus 1 minus, let's just leave it as is. Who cares? I mean, yeah, we can simplify it, but one could also argue that's for nerds. Let's just do the +1, the -1. That's easy. Let's leave it as y minus quantity, thank you, pen, y minus 2 squared. Yeah, I can multiply that out and combine like terms. Bleh, it's going to be a calculator problem anyway. Or maybe, I mean, I guess we could do this one by hand. It doesn't matter. The important part is the new calculus, not the old calculus. So let's see. Remember, when integrating with dy's, you got to use y limits instead. So y limits, we're going to go from bottom to top, because you know with x limits we always went from left to right. So with y's we're going to go from bottom, so we want this y value to the top, this y value. So we'll go from 1 to 4 of the width of all these rectangles, which is going to be y minus 2 quantity squared, dy, because our rectangles are oriented the other way. And again, you could punch this in your calculator, or you could do this by hand if you did the squaring. It'd be very easy to integrate, but I know you know how to do that. And punch that in your calculator, you'll get a value. Let's see, what other bits of advice do I have that I said aloud, I didn't write down. What did we say? If using y as independent variable, dy slice, need y limits. That's what we got. What else? What else? What else? Again, we could have done this one with x. It would have been painful. So I wanted to show you with y's. Okay, I think I'm running long here, so I know we got one more, and hey, only one video for this section, so that's nice, right? Let's take a look at the last problem. So I would like for you to pause the video and try to find this area. There are 2 or 3 different ways you can go about this. They're all not too bad. They don't take up very much space here. In fact, I think I have enough room on my screen. If I just cut it right here, I should be able to get all 3 of them in there. So let's have you pause the video, try it, come back. I'll show you what we end up with. All right, so first thing I'll just tell you, the final answer should be 16/3 no matter which way you do it. Let's see, I'm going to label my functions on here. So up top I have y equals 2. On the right side I have square root of x. And on the left side I have y equals square root of negative x, because we just have a reflection there. Since these functions are the same, there's a little symmetry here. You may have played on that. Your intersection points are 4, 2 and -4, 2. If you used vertical slices, so if you used dx's, so like you said, hey, this is one of my infinitely thin rectangles. So let's see, if we use dx, then let's see, if I'm going integral from, let's do top function minus the bottom one. And then let's see, we're going from the left side to the right. So, well, here's the thing. The bottom function changes halfway through. The bottom function changes at 0, so we got to stop at 0. So I would have to add to that the integral from 0 to 4. This would be the other side. Again, top minus bottom. So it would be the same thing, just the other square root function. Top minus bottom dx. So this is where the symmetry part comes in handy. You could say, and this is why I said there's really 3 ways to do it. You could say, or I'm going to double either of those and just abuse the symmetry. So you could say from -4 to 0, 2 minus square root negative x dx, or 2 integral 0 to 4, 2 minus square root of x dx, again, because symmetry. Either way, punch this in your calculator, do it by hand, it doesn't matter. You should come up with 16/3. If you wanted to do it the other way, so you did not have to combine 2 integrals or rely on symmetry, you could also use dy slices. So we could go, say, from here to here. So that then would have a height of dy. We'd have to talk about the width. So our width, we said, was the right function minus the left one. we would integrate from the bottom y value to the top y value. So just from 0 to 2. And then again, our inside there would be right minus left. Oh, but you know what? You got to be careful, because if you're going to do like square root of x minus square root of negative, that's not going to work because you used a dy slice. So we have an intermediate step. We have to solve both of these for x. So y squared equals x, and then y squared equals negative x. So that'd be negative y squared equals x. So again, doing right minus left would be y squared minus negative y squared dy. So 2 y squareds. That one's the easiest one to solve, right? Because then it's going to be 2 times y cubed over 3 from 0 to 2. Plug in your 2. 2 cubed is 8. 8 times 2 is 16. 16/3. And there you have it. Bounded area. Nice job, guys. All right. I can't wait to answer your questions next time. Sorry I went a little long.